Secondly, we discuss it from the viewpoint of the energy consumption. We suppose the initial phase angle of the source voltage is 0, so it is this. In resonance, the voltage and the current of the source are in phase, and the input impedance is R, so the current can be easily solved. We define Um over R as Im, the maximum value of the current, so it can be expressed as this form. Then we discuss the energy. The stored magnetic field energy in the inductor is this. And it's a function of time. Then we derive the electric field energy in the capacitor. We should know the capacitor's voltage UC. For capacitor, its voltage lags the current 90 degrees, so UC equals this. By taking advantage of the resonant condition and trigonometric transformation, we can know it equals this. So we can get the electric field energy stored in the capacitor, which is also a function of time. By observing the magnetic field energy and the electric field energy, we know that their sum is the electromagnetic field energy of the whole circuit. It's a constant value. By considering the definition of Im and the relationship between the capacitor's voltage and the source voltage in resonance, we can also get the electromagnetic field energy of the whole circuit in resonance equals this. Next, let's draw the waveforms of the magnetic field energy, the electric field energy, and the electromagnetic field energy of the whole circuit. Suppose the initial phase angle of the voltage source is 0, so the initial phase angle of the current is also 0. Capacitor's voltage lags the current 90 degrees. From the expression of the magnetic energy in the inductor, we can get this. The magnetic energy is a function changing with twice frequency and is always larger than 0. From the expression of the electric energy in the capacitor, we can get that the electric energy is also a function changing with twice frequency. Their sum of the two energies is a constant. What's the actual physical meaning of this? You see, if the magnetic energy and the electric energy is conserved in resonance, the reactive power Q of the whole circuit is exchanged between the inductor and the capacitor. And also, the source transfers the active power to the resistor directly, so the active power and the reactive power are decoupled. What's the advantage of this characteristic? Now, let's give the second definition of the quality factor. It equals 2 pi times the total energy of the circuit over the energy consumption in one period. For RLC serial resonance, it equals this. Im is the maximum value of the current. I is the effective value of the current. Capital T is the period of the resonance angular frequency, so the quality factor equals this. It's the same as the first definition of the quality factor. Now you can see that the introduction of 2 pi in the second definition enables the conclusions of the first and the second definition to be the same in any resonant circuit. From the second definition, we know that the larger the quality factor of a resonant circuit is, the larger the total energy of the circuit is, or the less the energy consumption in one period is.